Professor Osman Alagoz from TÜBİTAK, Turkey, with the presentation entitled by Approximation by Sampling Durrmeyer Operators in Weighted Space of Functions. If you are ready, we are ready to listen you.
Thank you so much. Do you hear my sound?
Yes, we can hear you and we can see your screen, but please make your presentation full screen with Ctrl L.
Sorry, I couldn't get.
Can you press Ctrl L?
Ctrl
L.
L. Okay. For what?
For making full screen.
Full screen.
Görünüm. Thank you very much. Now we are listening to you.
Okay, thank you so much. Hi there, participants. My name is Osman. I am an assistant professor doctor in Bilecik University. We are working on a scientific research project supported by TÜBİTAK, and this presentation was made by the authors you see on the page. These are my collaborators. In this work, we study approximation properties of sampling Durrmeyer operators for functions belonging to weighted spaces of continuous functions. We get pointwise and uniform convergence results of the family of operators and determine the rate of convergence via weighted modulus of continuity. We also studied a quantitative Voronozh-Kaya theorem to obtain rate of pointwise convergence. In the last part, we give an example by using some specific kernels which satisfy the theorems obtained. Generalized sampling series was first constructed by Butzer and his school in the late 1970s in order to reconstruct a function f with its sample values at some discrete points. It is defined by the equation labeled 1, as you see. Here f is a function from R to R for which the series is convergent for every x, and chi is called kernel, satisfying some suitable conditions. After that, Bardaro et al. Introduced the L1 version of generalized sampling operators in cited 5. They also define Durrmeyer modification to approximate functions belonging to LP spaces by replacing the integral means by a general convolution as in the form you see in the middle of the page. In Durrmeyer modifications, the kernels don't need to be same. In the previous page, you see the same kernels called Warphi in the series and in the integral. But as I said to you before, the kernels don't need to be the same. In the recent paper, which is cited in 16, Costarelli et al. Have constructed a generalized sampling Durrmeyer operators in this frame. As here, the kernel functions Warphi and PC satisfy some suitable conditions. So let me talk about some preliminaries. In generalized sampling series for functions having continuity property, sorry, I skipped a page. Yes, this page. There are some things that I want to talk about this page. In generalized sampling series for functions having continuity property, Generally, the space C to 0 R has been considered to eliminate the boundedness of the corresponding function. In a recent research paper, the authors considered weighted spaces of functions, although the family of generalized sampling Durrmeyer operators is defined for functions LP space. It is also meaningful for functions, for continuous functions as well. So this time we can talk about the preliminaries. Let me give you some basic notion and definitions about the study. Let's denote L21 the space of all Lebesgue integrable functions, and by C0 the space of all uniformly continuous functions. Let's consider two functions which is called kernels, Varphy and PC, such that satisfying the conditions which is labeled 1, and then we give the definition sorry, we give the definition, the algebraic moments and the absolute moments of these kernel functions, as you see on the page. And we have a remark: as a result of the assumptions of the sampling Durrmeyer operators, we obtain the first result. The operator take 1 to 1, where here 1 denotes the identity function. In the second item, we obtain a result of absolute moment of Varphy kernel and also PC kernel. Now, it's time to talk about the weight function. A function rho is called a weight function if it is positive continuous on the entire real axis R. In this study, we consider the weight function as rho x equals to 1 to 1 plus x squared. Here we give some specific notation about function spaces. As you see, B rho R, the space of all real functions whose product with the weight functions rho on R is bounded, denoted by B rho, and some other subspaces of it. We can easily see that B rho R and the subspaces of it are norm space with the norm of F according to rho. Here we also give the definition of the weighted modulus of continuity for functions F, which are element of C rho. The subspace of B rho is denoted by omega, big omega, and given in the equation labeled 3. In this lemma, we recall some properties of weighted modulus of continuity. Let delta is bigger than 0 and x is element of R. Then we get these 3 results. In the first item, omega is a monotonically increasing function. In the second one, omega goes to 0 as delta goes to 0 for functions f, which is an element of C rho. And in the last item, for each lambda is bigger than 0 and f, we have this inequality. On the other hand, quantity of absolute value of y minus x with respect to delta directs us to a piecewise function, piecewise inequality, sorry. So we get the main results. Here is a proposition which helps us to obtain the next main theorem, where Varphy and PC, the kernels with alpha equals to beta and equals to 2, and rho is the weight function here. It is a spatial inequality, but it's very useful for us. It is a nice proof process by using the definition of sampling Durrmeyer operator and the definition of algebraic moment and absolute moment of the kernels and some other basic algebraic operations. We can get the result. In this theorem, we show that our operator is a linear operator from B row to B row. We omit the proof details here. And this is the theorem about the pointwise and uniform convergence of the operator, which is one of the main theorems of the paper, of the study. And the proof pages, because I don't have enough time, I am skipping these pages. Here another theorem, and this theorem gives us an upper bound between the difference of operator and the function of f, and we again the details of the proof. We get a remark. By using Taylor expansion of a function f, such as in the equation 8, and the error term function, together with modulus continuity, we can obtain a new inequality form given in labeled 9, as you see in the bottom of the page. Now we can state the Voronovskaya theorem. Let var p and pc be the kernels with alpha and beta equals to 3, and then we have this result. We omit the details of the proof. In the last part, we get here, I give you an example which satisfy the results given in the theorems. Firstly, let's give the definition of the central B spline. It's a spatial kernel function of order 3. Here you see the definition, which is labeled 10. If we write more explicitly of the form of this kernel, we can get this piecewise form, which is on the top of the page, as you see, and you also the graphic of this kernel. We can easily understand it satisfies the assumptions which is given in the theorems. For example, the sum of the series equals to 0. We can calculate this calculation using MATLAB software. So let's go on. Here we take another kernel function by taking characteristic function, which is defined on the closed interval 0, 1, and as a result of choosing these spatial kernels, we get Durrmeyer sampling type series becomes like this. So now this is time to choose a function. We choose a weight function. Here we define fx equals to 1 to 1 plus x minus 2 square. Then in the operator, as you see, we have some constant, as you see, omega. We take these omega values 5, 15, and 45, and see the results according to these omega values. What will be the graphical approximation results? In the next page, you will see the results. between the operator and the function we choose. If we take omega equals to 5, the result is here. If we take omega equals to 15, the result is here. And if we take omega is 45, the result is like this. So these are my references which we used. Thanks for watching.
Thank you very much, Professor Osman Alagoz. I would like to give my thanks for your valuable talk. Now let me ask the panelists and attendees about the questions and any comments. And now I'm seeing a question. We have a question. It says that, why do you have -2 in the denominator of the weighted function?
Why do we have -2 in denominator of the weighted function? It satisfies the condition. There is no any reason not to choose this function. I don't get exactly the question. Why?
If the attendee wants explain one more time his or her question, we can wait a little bit. And also, let me ask my question one more time. Is there any comment or question, another question for Professor Osman Alagoz? Or this anonymous attendee, is this anonymous attendee satisfied from this answer? We have one more explanation from the same attendee. Can you see the question? Let me read. Usually we have 1 plus x squared. In this case, you have -2. How do you choose your weighted function?
Yeah, we don't have to choose every time 1 plus x squared. We can take any raw function instead of x. So here we take x minus 2 instead of x to make a different result. And also we are working on some other different weighted function graphical results, but it didn't finish yet, so I couldn't add the presentation. So we are still working on it, and when we finish it, we are planning to submit this paper, and maybe if we have a chance to publish it, we can prove the details more and more.
Okay, thank you. Also, the anonymous attendee says thank you. We are also recommended to follow your researchers and academic publishing after today. So I think there is no any question. I would to say thank you one more time to you for this nice presentation, Professor Osman Alagoz. Also, we want to give our thanks on behalf of our organizing committee for this nice contribution. Now,